Hello and thank you for watching our presentation. My name is Tina Eskandarian and I'm here with Matt McMillian and Daniel Strong. For this spring semester power analysis course, we decided to go with Design Project 1, which is called New Load. An overview of the presentation today, we will be going over the objective, design parameters, calculations, our official design, any recommendation, and the conclusion. The objective for this project, Metropolis Light and Power, is to have new loads on the eastern portion of their territories, and we were to design a new substation called Tulip to accommodate all the loads and any sort of fault. We were to assume a peak load of 70 megawatts and 20 megavars, and we used power analysis through Power World to examine all the calculations and come up with the best result to accommodate for the loads. Now I'll be turning it over to Daniel to continue on with the presentation.
So for our design, we initially had to come up with various parameters, to even get started. So right here you can see the different line lengths that were used, and various numbers of those were used for our design durations. And here is the actual line parameters and the line costs. So for our design, we only needed to use 161 kV lines and a 69 kV line. However, our primary load, Tulip, was a 69 kV load, so we had to create a separate bus that was a 138 kV bus that we then transformed down to 69 kilovolts. And again, you can see all the different lines, only from Rook to Cardinal, were used for our design. For our calculations, obviously we just had a few given equations. So the first one was for S, obviously equals VA conjugate. And in for our lines, since they were lower voltage, we only had to worry about the series parameter. So we calculated the inductance L and the resistance R of the lines to come up with the impedance. And those wound up being in per unit values. And finally, the transformer that was used, we were given the impedance, and that was 0.0025 plus J of 0.07, and that was also in per unit. So we had to go through various design iterations, and several of which did not work, unfortunately. So for this first iteration, we had Tulip to Olive, Tulip to Birch, and Tulip to Plum. And so for all of these, we had to do a contingency analysis and see what faults would arise. So for all of these, the biggest problem that we ran into was the Lemon 138, Lemon 69 transform. When that would be taken out, our Cedar to Olive line would become overloaded. So here you can see that line is overloaded. And so for the next one, it was actually even more overloaded. And for that one, it's the same as this, other than that we took out the Tulip to Birch line, and that actually made the overload worse. So here you can see that the overloads are actually getting a little bit better with these new iterations. So this first one, we did Tulip to Olive and Tulip to Elm, and again, taking out the Lemon transformer, was the biggest problem where we get our line faults from. And then our final failed iteration, you can see there we actually used 3 different lines, 2 of which were 69 kV lines. We had Tulip to Olive, Tulip to Cedar, and again Tulip to Plum. And that was the best one out of the failed iterations, but it's still, we were getting overloading on our line. And So that brings me to Matthew, who will be going over the successful iterations that we were able to go over. Yeah.
So ultimately we decided that we needed to have an additional line from cedar 69 to olive 69, because this was a line that kept getting overloaded, so it needed additional line to be able to carry that power across there. So that's what we did in all 3 iterations of working designs I'm going to go through. We did have one other design that was working, but we are only going to talk about the top 3 that we're considering for recommending. So as you can see from the table next to the picture, on this design we use tulip to birch, tulip to plum, and cedar to olive. Now based on the values of the power rating with the 69 kVA, the 53.13 MVA, that turned out to be our middle range of conductors we could use. The best one was, so we had 3 out of the 69 we could use, and the 53.13 MVA was the middle best one. We use this one ultimately because it does cut down on cost, and the feeder is still able to operate under all contingencies. So the next design, we still kept that cedar to olive, but we switched it up a little bit. We got tulip to elm, and then we used tulip to olive. And with all of our 138 kV lines, we did end up using the best conductor we had available to us, because that conductor had pretty much all the load that tulip would, our new load, tulip 69 load, would undergo. So it was carrying all that load, so we needed the best line in order to handle that. For our last design, design 3, we used tulip to plum and tulip to olive. Then finally, based on the table you see here, on the 3 designs, so the second table, we have the total losses. So as you can see, design 1 had the least amount of losses throughout the whole entire circuit. And then the next table, the line cost, that gives you a number of all the lines we used combined, how much that costs, because the lines varied and the cost between the lines varied. One thing that I didn't take into this table was the transformer cost and the bus cost. The reason why I didn't put it into there, because they all use the same price, and it was ultimately factored into our total cost. So the money saved that value is the money you saved based on how less your total losses was compared to the original design. So between design 1 and 3 we're kind of just deciding which one we'd recommend. Design 1 has a better total loss, but design 3 has a total cost being less than design 1. So we didn't look at the money saved, and between that, you see that the total cost is magnitudes bigger than the money saved. So in order to save that money back for having a lower loss, it would take a lot more than 5 years to do so. So we ultimately decided that design 3 would be the best design for adding this new load and eliminating the contingencies. So in conclusion, we had Metropolis Light and Power. They gave us a circuit and they wanted to add a new load. So we went through different design processes to figure out which way would be best to design this load. We did calculations for our lines and for how much the lines could handle, what the impedance of the lines, and the transformer values were given, the bus was given, and then ultimately we ran those analysis on PowerWorld and decided that design 3 would be the best to recommend for Metropolis Light and Power. Thank you for your time. If you have any questions, please comment in the comment section below this video. Thanks. Bye.